Hello, listeners of the Mad Scientist Podcast. I'm your host, Chris Cogswell, here this week with a special guest, Chris Birkenbein from the Dash of Science podcast, or actually a Dash of Science podcast. Man, the grammar is not my forte today, man.
It's you can mix it back and forth. I usually drop the A when I'm talking about it, but you're right, it does have an A in the beginning of it. So
yeah, it's funny when people ask me about this show. I'm always like, oh, the Mad Scientist Podcast, and they're like, oh, Mad Scientist Podcast, and no, the Mad Scientist.
The Mad Scientist. Yeah, I have to be careful because there's a food scientist who started a blog like 2 years ago, and it lasted for 1 year, but that site is still up there, and so that one's just Dash of Science, which is why I got an A in mine. But man, a little tricky thing. So hopefully he doesn't come back and decide he wants that back.
It's the hard part of doing podcasts.
Mm-hmm.
So Chris is actually a range systems engineer for NASA.
Mm-hmm.
He, like I said, does a really great podcast on science, and just generally is kind of a very knowledgeable, cool guy that I wanted to have on the show. So, Chris, why don't you give the listeners a little bit of intro on you?
Sure. So, like you said, my name is Chris, and I have a podcast about science. And I love talking about science, all types of science, with anybody who will. My background is I have a undergraduate degree in applied physics. And I'm about half a paper away from my master's degree in space studies, specifically space engineering, just, engineering constructs, stuff like that. And I'm hoping to continue that on into a PhD of some sort at some point. But, you got to get that around to work. But for my job, I work at NASA Armstrong Flight Research Center, which most people, even in NASA, are like, where's that? It's because it used to be called Dryden Flight Research Center. And that's a place where all of the astronauts were at Edwards Air Force Base before they became astronauts doing, flight test stuff. So the shuttle landed here a couple of times. But out here we do mostly aeronautics instead of space stuff. We do deal a little bit like we did some stuff with Dream Chaser from Sierra Nevada. And we got some stuff with Boeing CST-100. They might land here on their flight tests. But mostly we do airplanes related stuff. Right now, some of our big projects are working on like quieting the sonic booms for going Mach, which a lot of people don't realize is a big deal unless you live outside of an Air Force base doing testing. There's many shattered windows stories. We have special insurance just to go out and fix people's windows when need be. But yeah, so the hope is that you can get that quieted down enough that it becomes less a nuisance to people, and then you can start having hypersonic corridors for travel, for much faster travel. So
very cool.
Yeah.
Oh man, that honestly is such an interesting point about, like you said, making air travel faster. Well, once you hit that sound barrier, right, you're going to have these, I know I personally, grew up in New York City, Staten Island. We're Newark Airport Airport is right near us.
Mm-hmm.
And so, a lot of my memories of being home are, hanging out and playing around and whatever, and then stopping to look at a plane fly overhead.
Right.
And just the noise, like that constant noise of a plane going past your house. It's, when I got to school in New Hampshire, like just how quiet it actually was without airplanes always going by me freaked me out, besides just the darkness too, like, going from New York to the woods, essentially, at least for me. So that's very, very interesting. So I guess with this kind of aeronautics and with space science generally, it's such a huge field, and so many people are interested in getting into it. And I actually get a lot of questions, I know my cousins or, friends who have kids or whatever will ask me, they'll introduce me as, Chris, and he does a science podcast, and he's kind of a science, he's a trained scientist and everything.
Mm-hmm.
And the kids are always like, oh, cool. What do you think about space? And I'm like, well, I did a lot of science on rocks. And then they're like, oh, okay. And they go back to their Game Boys, like I'm the disappointing scientist, I guess, that they know. What's kind of that academic progression for getting involved, say, in kind of space or science research of that sort that has to do with, rocketry, space, everything else?
Well, let me start off with just saying that pretty much every science is utilized when you're doing space. If you're taking that path, right? If that's your interest, even rocks. When you get down to it, when you like look at like asteroids and stuff like that, that is geology. It is 100% geology. Which, as a younger person, I was very disappointed to learn because, like for me, geology. I mean, there's a lot of memorization of. It's kind of like when you're learning chemistry in the beginning, right? And you're learning chemical formulas and compounds and stuff. It's just a lot of memorizing names at the very low level. And I don't do well with memorization. I do well with math and a process. That's why I love physics, because if you got F equals ma down, you can pretty much derive most anything else you need from that.
Right.
But yeah, so for me, I was about 8 years old when I decided that I wanted to work for NASA. And of course, I wanted to be an astronaut, like many young kids do. And I'm still hoping to be. I applied this last time, knowing that I wasn't quite qualified yet, and I plan on applying next time. So cross your fingers for me. But my path was a little, I guess, curvy, for lack of a better word. So I went to school initially for electrical engineering, and I ended up going from there to the military to serve time, because a lot of people that were astronauts had a military background. And then from there, I came back out, tried to go back into electrical engineering, and realized that there's just so much formula memorization in electrical engineering and not a lot of fundamental understanding of why those things worked. So I jumped into physics, and I love physics, but then you lose your hands-on part of that. So that kind of led me into a new program at my school called Applied Physics. So since the program was new, I was lucky enough to be able to like hand pick which engineering courses I wanted to put into my degree, which is an amazing benefit, let me tell you that. But it's also a little scary, because you're not quite sure if you're going to build something that's useful or you're going to get out with a degree and nobody wants you, right? But the good thing about physics is it does give you a broad understanding and problem solving, as a lot of sciences do. And so it's pretty easy to get into most engineering fields. So if you like science and you don't have a problem with math, I definitely recommend physics as an undergraduate degree, because you can branch out into pretty much any other type of science from there, I think, depending on what you want to do. And as far as getting into NASA goes, the hardest part about getting into NASA is it's a government job, a federal job, and that's hard. But if you find, you go on USA Jobs and you look in there, they'll have all sorts of opportunities for internships and pathways that you can use to get in there. And like I said earlier, really, any science or any engineering is going to be able to get you a job in that field. It just really depends on what your interests are. So I don't think that it's limited by necessarily a specific path so much as it is by what it is you want to specifically do, if that makes sense.
Yeah, absolutely. No, it definitely does. I mean, it's a lot of the research. So when I first got to grad school for the PhD, my professor and I had kind of a list of ideas that he wanted to work on. Mm-hmm. And then I had kind of a list of ideas that I wanted to work on. And we sort of tried to, you try to put them together, right? Mm-hmm. And so, but a lot of the ideas that he was working with are a lot of the applications that kind of the first early, grant applications and kind of, presentations and whatever. A lot of that early stuff that we focused on was, this would be good for space travel, or this would be good for confined areas, right? For, CO2 conversion to oxygen, say, for, prolonged travel or prolonged confinement someplace.
Sure.
Or, heat transfer materials or radiation shielding. All that kind of stuff was really an initial thing that I had never even considered being, I wanted to work on, nanomaterials. Right. And obviously at the, when you first get into that kind of world, you're thinking like, oh, I want to build, I want to make a nanorobot that'll block out the sun.
Right.
That's your first kind of
and
thing.
And you get into that and you realize that they're making springs, like nanostructure springs, and that's the extent.
Right. Yeah. You're like, oh my goodness, we're the farthest we are is a nanospring. And, it's like one guy at Bell Labs and, it's very, very interesting. So it's cool though, to think of all the applications and stuff. And you're right. I mean, it's part of the reason that I think people want us to try and fund NASA further, or want to start looking at, going to Mars, going out there, going back to the moon. Because there was, there's just so much of our science that came came from those projects.
Mm-hmm.
You know, and I mean, it's just because, you know, science is hard to fund without the government.
Right.
So,
especially like beginning level science that doesn't have any necessary commercial payoff, right?
Right. You have nothing there until you're in space and you realize, oh man, all this stuff we worked on is, you know, look how cool Velcro is.
Right.
Right. So, you know,
are you familiar with NASA Spinoff?
No, actually. So what is that?
So NASA Spinoff is an annual publication that NASA does that really just highlights all of the technology and stuff that's come out of some form of NASA grant or work that is being used commercially in other aspects outside of space. It's really an amazing literature to go through because, I mean, you've heard, you know, what do we get? Like, why are we going to space? What does that do for us? A lot, a lot that has nothing even to do with space.
Yeah, and you don't realize it in your daily life because, well, you know, parts of this argument, I love the two ways this argument gets used, right? The first one is, what do we get from space? Who cares? Whatever. The other side of it usually is, I don't understand how we made the strides to get this technology, therefore it must have been aliens. Right? Like, yes. And in both cases, the answer is no. NASA has been working on this for years, and it just so happened that it finally came out to something cool.
Yep, exactly. And it's probably been, you know, the DoD also, you know, has a lot of stuff. DARPA. What I find amazing is they'll, like with DARPA specifically, I've had the both the fortunate and unfortunate opportunity to work with them on a couple of projects, and their mentality is just it's completely backwards from I think NASA is, and whereas their most important item on a project is schedule, right? They have a very limited schedule, and they will throw all of the money in the world that they can get their hands on at it, but once it gets to that point in the schedule, it's just done. And so they'll get great strides in this technology, but it won't quite be enough to be actually practical for anything, and then they'll just stop, and then it'll just sit there for months or years until somebody else comes across that research, and then they move on it, and then it becomes this, you know, public known entity that is just amazing, but we've actually known about it for a decade. So
that's really interesting. I had never even, you know, you hear about that with, say, in other fields, right? Like in my own field, you know, we first discovered clays for catalysis in like the 1920s, and then we stopped using them because we were like, well, we just can't get enough speed out of these dang things. They don't have any pores,
right? And
then in the 60s, all of a sudden we discovered zeolites. Or we discovered how useful zeolites could be, and suddenly people started caring about clays again.
Right.
And so it's like, you know, it's an area where you do have this kind of fundamental, it looks like a big jump in knowledge,
right?
But really it's just kind of been sitting on the back burner, right? What would you give as an example, I guess, of something like that?
Well, something that's maybe not necessarily out yet, if you think about like, I mean, I'm sure you're familiar with the problems that we have with nuclear energy in this country and in the world about misunderstanding of safety and stuff. And that's affected a lot of the things that we're able to do in space with nuclear propulsion. So we have something called nuclear pulse propulsion, and we aren't using it yet. But when it becomes something that we're actually using, I mean, this has the capability of getting us from, you know, here to Proxima Centauri in 100 years. And this is something that we've known about since the 30s. In fact, we've had various different experimentations with it. The reason why we don't do it anymore is because the very initial, you know, tests would have required major nuclear fallout on ignition for launching these into space. Obviously, we've moved past that, but there was such a huge, you know, backlash from the public about safety, and at the time, rightly so, but it's kind of stuck around to where we haven't made any further actual physical progress in these things, but like the math and the knowledge and the theory is all there. So we're going to, at some point, you know, have this propulsion system that just blows everybody away. And, you know, someone's going to be like, oh, yeah, aliens. No, we've known about this for near 100 years now.
Right. I was going to say, I can't wait for the Ancient Aliens episode on that.
I know,
really
right?
Great. You know, hopefully we won't shape the craft like a bell.
Right.
We'll really be getting into trouble there. So actually, that kind of brings us to the topic of why I originally reached out to you to have you come on. Is this idea of 0 point energy.
Yes.
Right. And that kind of how we can use it for propulsion. So for the listeners out there who, you know, so we've kind of been making veiled, I want to say veiled threats, but that's the wrong term here for this. We've been making veiled references to this idea in a lot of our episodes on To the Stars Academy. and I kind of gave a very sort of kind of a halfway explanation of kind of how it works.
Mm-hmm.
And frankly, I mean, part of that is because it's very complicated and it's hard to wrap your head around generally. And also just because, I kind of wanted to get someone who had a bit more of a background in this to come and discuss it with us.
Sure.
And so the way that it's been used in kind of the fringe science, world right now is that it is a potential way to generate both infinite energy, right? Which that's how we kind of came at it was, well, that just fundamentally breaks the laws of thermodynamics, right? You can't get anything for free. And then also that it can be used, therefore, for extreme propulsion systems or very fast travel through space. And so the argument has been made, let's say, by some famous scientists or famous science figures, let's say, today, who are part of, say, To the Stars Academy, but also by, people like Bob Lazar, right?
Right.
So who, I'm sure you know this, but basically, claims that he was at Area 51 and worked with alien propulsion and yada, 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 right? So first off, I guess, kind of how would you describe how would you describe 0 point energy to someone who knew,
Sure,
a high school level of physics?
That's a hard thing to do, because when we're talking about quantum anything, first of all, we see all these articles, and we know how articles work. Somebody writes a good article, and then somebody else makes a ridiculous title for it to get you to click on it, right? So we see quantum attached to all these amazing, actual, real things that are going on, and it becomes like this magic word. But when you get down to quantum mechanics and quantum physics in general, everybody's got to understand that to really understand this, it's not that it takes a really smart person. It just takes somebody who had the time and money to invest a couple of years worth of academic study, or even on your own, right? If you go that route. So there's nothing wrong with not understanding it initially, but you can't trust. Don't trust somebody because they're a scientist. Trust somebody because they lead you to valid sources, right? We trust research. We don't trust the scientist. That's what I always say about everything. So, because you'll find a scientist in every field that will have, to put it politely, wackadoodle ideas or woo ideas. So that it's not impossible to find somebody with valid credentials with invalid ideas.
Right. I actually love on Ancient Aliens. They have a guy who is a heart surgeon that they tote out sometimes, and they're like, oh, doctor, whatever, heart surgeon, and he's talking about, how it was impossible for the Egyptians to build the pyramids, and you're like, what do you know? This isn't a heart. You know what I mean? Get back in surgery, dude. Right. Get out of here.
That's a very true point. But to get back to your question, so when we're talking about 0 point energy, essentially quantum field theory predicts that there exists a certain amount of energy, right? The lowest possible energy that the quantum mechanical system can have. And then in classical, you've got a minimum energy of that system, and there's a difference between these things, okay? And so that's kind of one of the fundamental problems that exists in physics today. And when you're talking about quantum physics, that lowest energy point, it fluctuates. And it fluctuates because of the uncertainty principle. And so essentially you're looking at the differences in those energies, and that's what that 0 point energy is. I don't know how to explain that in a better way than that, but if you just think about it as the differences in that point for the energy that it can have as it's fluctuating, and as well as the difference between the classical and the quantum states.
So, okay, so let's do some quick definitions for the listeners here.
Sure.
Right? So a quantum mechanical system is, in this case, we're talking about a field, like,
sure.
Imagine you have a box and it has inside of it particles, and then you evacuate the box, right? That's the system we're talking about here. An area with, is that the correct understanding? My correct understanding here?
Sure.
That we're getting to a perfect vacuum, essentially, that should have the lowest possible energy state that can exist, which is absolute nothing at near absolute zero, or at absolute zero.
With the caveat of understanding that we don't necessarily have a perfect vacuum anywhere, but yeah. I mean,
right.
So, like, as an example, you have, say, the electromagnetic field, right? And And through theory, it's estimated that this has, I think it's 10 to the 112 ergs per centimeter cubed, which is about, I think that's, what is that? And it's pretty close to joules, I think, if I remember correctly. But essentially, this is 10 with 112 zeros behind it. That is a massive number, right? Mm-hmm. And then when you look at like analysis of the expansion of the universe, we experimentally get out through observation that it's only 10 to the negative 8. That's a huge, huge difference, right? Mm-hmm. I mean, you're going 112 zeros to, a decimal with 8 zeros in it. So this is kind of that fundamental problem that's unsolved. And I think this reason is what leads to a lot of the, I guess, the woo, for lack of a better word.
Okay, so the disparity here too, again for listeners, is based on the way that we understand the universe through the lens of quantum mechanics.
Mm-hmm.
There is a certain minimum energy that has to exist in the universe,
right?
Even in the case of the lowest possible energy in a system. In standard physics, though, before quantum mechanics, the kind of physics that we use to explain big objects,
mm-hmm.
but which really doesn't work for small objects anymore,
right?
There is another energy. And so what people who espouse zero-point energy as a theory are saying is that both of those theories have to be correct simultaneously. And, there has to be some obvious pool of energy someplace that we can pull from that explains this disparity in the energies observed versus expected.
Right.
Right. So, and that's kind of the fundamental, I think, part that we didn't really get to last time. I mentioned that for this to be true, you essentially have to get rid of a fundamental part of quantum mechanical theory.
Right.
Right. You're basically working, I think I said that it was like the voluminous ether theory when we first talked, when I first talked about it on the show, but it is on its own kind of a holdover idea. And so you're trying to kind of fit these two things together that don't even exist in the same realm.
Sure.
Right. It's kind of, for a simple explanation, it's like trying to put, a Chevy, trying to put the door of a Chevy on a Ford. Right. You can kind of get it to work, but it's going to look dumb.
Well, the best way that I have that I think really explains this is I think people come at, because we talk about a unifying theory that's going to unify, classical and quantum, right? And we always have this understanding that, like you said, both of these things are correct and we're just not combining them together. But I don't think that's necessarily true. And the perfect example that I've always come up with for that is Newtonian physics versus relative physics, right? We use Newtonian physics in everyday stuff because it works. Even though we know that Newton's theories aren't complete. Those equations don't cover everything. But if you're talking about the speed of a car or the speed of a baseball on the surface of the Earth, they get us close enough that we can't measure the distance in everyday life. But those formulas break down when we're talking about like satellites and GPS doesn't work with Newtonian physics. You have to use relativistic physics, but that's much more complicated. So why would you do all that complicated math that gets you the same level of precision that you can perceive when doing something at non-relativistic speeds, right? So I think that might be potentially something that's going on with, classical versus quantum. First of all, there's stuff about quantum that we obviously don't understand yet, but also classical still gives us answers that work. And the importance of having these functions and these theories that we have is that we're able to make predictions, correct? So if we have something that allows us to make correct predictions within the context of what we're doing, then it doesn't necessarily matter if it's 100% correct or not. So once we figure out how quantum theory works like completely, I suspect that it'll be very similar to what we do with Newtonian physics. Yes, we know that that's not 100% accurate. That's not the whole story, but it's easier to do and it works for what we're doing. So that's kind of where I see that going, if that makes sense.
No, absolutely. It's the difference between using a hammer and a sledgehammer. Right? The hammer is good for smaller things than the sledgehammer is. They both give you the same result, maybe if you use them, but one of them is better for tearing down a building than the other one is for,
Correct.
So I guess because there is some idea though about this being essentially like a perpetual motion kind of
Right.
system, right? Because again, they're arguing that there is this,
Mm-hmm.
they're arguing that there is this, this difference in energy has to be, we have to be able to get it somehow,
Right.
right? But again, as we've kind of pointed out, it's almost a fundamental misunderstanding of the two things, right?
Sure.
I mean, I think, it's like there's a stupid thing going on Facebook right now, which is like, you steal $100 from a bakery, you then buy $70 worth of bread, and they give you a $30 discount. How much money did you actually steal from the bakery? Right.
Yeah.
And we're just not going to get into it right now because it's frustrating to no end the answers that I've seen.
Yes.
But
I would just like to point out that I hate the very fundamental math questions that are posted on there that are deliberately stated in a way to make everybody feel stupid. That doesn't help anybody.
No, it's not good, right? Like math is hard enough for some people. Like don't make it worse with crazy questions like that.
Mm-hmm.
But it's kind of like, you lost $100 in your wallet and then you find it again and you're like, oh, I made $200. Right. And it's like, no, you didn't.
Yeah.
Like, you lost it before and now you just found it again.
Yep.
So there still has to be a place where this energy is coming from for us to pull it out again.
Right.
But some of these ideas have now taken on kind of a life of their own where people are starting to argue that we could use these for propulsion.
Right.
And so the essential way to do that would be, right, you just find a way to harness the energy somehow, and then you just use it to turn an engine.
Sure.
Right? Or you use it to push a ship somehow.
Yeah, there's a couple of different aspects there. Like I assume you're trying to get into like the Casimir effect, and like with the EM engine that was big news a while back, and like that kind of stuff, right?
Absolutely. So first off, I guess explain as best as anyone can.
Sure.
Explain kind of the Casimir effect.
Well, let's kind of take a step back because we're talking about how like the idea of perpetual motion energy. What I find interesting is that the same arguments that disprove perpetual motion and unlimited energy really are the exact same arguments that invalidate these talks about pulling. So if you talk about entropy, right? Thermodynamics is not the simplest part of physics. So entropy is essentially the degree of randomness within a system, right? It's the measurement of the unavailability of energy. So when you convert whatever energy into mechanical work, you're reducing the availability of stuff that you can turn into energy, and thus you are creating more entropy. So the universe tends towards disorder, which means entropy in a closed system kind of always increases. So once you get to perfect equilibrium, you can't pull anything out of that system. And kind of what I like to think about we're talking about like 0-point energy, right? So on my show, we've talked a lot about like pressure and space vehicles. So when you pump a gas into a closed vessel, you increase the pressure. And when there's a mismatch between the pressure inside and outside, you create this differential that becomes very dangerous to essentially puncture that vessel because all that fluid mass is going to then rush towards, from higher pressure to lower pressure. But when that movement happens, we now have the ability to convert that into mechanical energy, say like through a turbine. The same thing goes on with electricity, right? Voltage is a measure of the imbalance between two areas. So when you create an imbalance, those electrons flow, and now you have electrical energy. But the thing in both of these examples is it doesn't matter how much pressure you have. It doesn't matter how many electrons you have. What matters is the difference between the 2 points. So even if there is this insane amount of energy within the quantum field of a vacuum, that vacuum overall is the same everywhere, and thus it's already in equilibrium. So extracting energy from that becomes the problem, as you said, and that's why.
That's actually really interesting. So I think, so for a simple analogy with physical things that you might feel for our listeners, because I know I need the same thing, it's like saying, if you're 20,000 feet below the surface of the water, you're at a certain pressure, but that pressure is the same everywhere horizontally.
Right.
So you don't feel a wave.
Exactly.
Right. You don't feel a wave. Whereas if you were at the surface of the water and you had a sudden surge of pressure that created a 20,000 foot pressure of water, wave, you would feel that wave, right? Because it's going from that difference between the two. Yeah, that's actually a hilariously elegant answer.
It's really simple, right?
So those arguments.
So as a whole, this is things at equilibrium. So the only way that we could ever draw anything from this is we would have to introduce some form of disequilibrium at a specific point, right? And that's where the Casimir effect really comes into play. So this is, if you bring a pair of conducting plates close together, and by close, I'm talking like the biggest distance I've ever seen experimentally is 2 micrometers. So that's 10 to the negative 6, right? We're talking really, really close. And so when you do this, some of the virtual particles will be left out between them. So if anybody's not familiar with virtual particles, so there's a fluctuation basically that shows some of the characteristics of regular particles, but they only exist for a very minute period of time, which again is defined by the uncertainty principle. Kind of the existence comes from perturbation theory, that ordinary particles interact by exchanging these virtual particles, right? So I guess without diving off to the deep end of quantum mechanics, the uncertainty principle is just one of the ways of asserting a limit to the precision that paraphysical properties can be known, right? So that whole, you know how fast it's going or you know where it's at, but you can't know both exactly. So this kind of all comes out into what defines the existence of these virtual particles. And again, in quantum mechanics, this is how 2 particles interact, like how they exchange, like in this particular case, momentum. So by doing this, you're lowering the vacuum energy in that region. It creates basically the same like a pressure differential with an actual measurable force, which will pull the plates towards each other, or rather push them towards each other, depending on how you look at it. And that is a mechanical energy, right? You've now taken mechanical energy out of this system.
Sure. Yeah, absolutely.
But the problem with this is, like any other, I mean, we've all seen the various different types of free energy or perpetual motion machines. So like if you talk about a rock, you tie a rock to something and you drop it and gravity pulls it down and you use that mechanical energy to do something, right? But in order to start that thing over again, you have to get that rock back up to where it started, which takes energy. Same thing with these plates. If you want to repeat this, you have to now separate those plates from each other. And that takes, coincidentally, the exact same amount of energy that it releases when it comes together. Except for we live in reality, and in reality, everything's messy, and we lose energy through thermal energy and these other actions, friction, whatever. So it's just like the Carrot engine of trying to get a 100% efficient engine, right? The best case scenario is that you're able to get 100% of the energy out of this system than it takes to set it up, and then you're at net zero. So you're never getting more energy. And this is I never want to say that nothing will ever be disproven, because I don't think that's a very scientific standpoint, but this is one of the fundamental physics properties that has been tested enough throughout the history of mankind that I feel that it's pretty solidly tested, at least within the confines of our system here on Earth, right?
No, if the second law of thermodynamics gets disproven in our lifetime, things will be a lot worse.
Every physicist will just throw their books in and go home and start over.
I was gonna say, I don't know what any of us will, our fridges will stop working. We'll just, freaking out. Like, no, man. So I guess I have a couple of, and maybe these are too deep, or maybe these are too kind of, So, okay, so you have these 2 plates here that are sitting next to each other. Mm-hmm. They're interacting by exchanging virtual particles.
Right.
The particles that are releasing the virtual particles, are those losing measurable energy?
So when you're dealing with interacting with virtual particles, you got to understand, because of the laws of physics, because conservation of momentum and conservation of energy, you can't, say, transfer momentum into a virtual particle without getting a real particle off the other side. And that real particle is going to contain all of the energy that you put into it, right? And it's basically, that becomes the propulsive grain, so to speak, at the end of it. So there's no way to put energy into that virtual particle and not have it come out somewhere, which is actually part of the ideas that some people have, like behind the EM engine.
So. Okay. All right. So the idea, okay. So still though, the idea is that you have this closed, if you have a closed system where these 2 things are interacting, energy is still leaving.
Right.
Right. Okay. Got it. Okay. That makes perfect. That, I mean, it makes sense. Not perfect sense, but it makes sense.
It's
right?
as much sense as we can have in a 60-minute podcast, right?
Right. Well, this is precisely why I decided that fluids was the smallest I wanted to get.
Mm-hmm.
Right. Like, I mean, nanoparticles are fine. We're starting to get kind of weird,
right?
But it's not weird enough that I'm, scratching my head all the time.
Mm-hmm.
So how are then, I guess, so the idea here for these people would be this Casimir effect suggests that for them, at least, they think, well, there's this energy in their minds is coming from this disparity of the 0 point field,
mm-hmm.
and therefore can be pulled out without any loss of energy to reset the system.
Right.
But obviously, what we're saying is that no, that can't be the case.
Right.
And in fact, experiments have proven that it's not the case.
And usually the problem comes into not properly bounding the experiment, if that makes sense. So we talk about a closed system, right? And that means you put these bounds on the system where you're not taking in any energy or releasing any energy outside of these bounds. So usually what happens is they're bounding their system improperly. So we are putting in momentum into these virtual particles, and these virtual particles are popping out real particles outside of the system that they've defined, and thus to them they have thrust.
Got it. Okay, so and for listeners here, if we haven't already lost you, the way that an example of this kind of at the bigger scale would be, you have two cars that crash into each other, and then you have three cars. One is stopped ahead, and then another one is stopped in the middle, and then a third one is coming from behind those two really quickly. It crashes into the second car, and then the second car goes flying and crashes into the third, where they all stop.
Mm-hmm.
If you define your system as just those two cars, the middle one and then the last one that's coming at speed, it looks like you've transferred energy and are propelling the system forward. That second energy car is going, but you're like, well, wait, we lost energy somewhere there. Right at the end of this whole thing. What you're saying is that, no, you need to account for all three cars because those are the three things that are actually interacting.
Right.
And so they're missing the boundaries of that physical system.
Exactly. And the other problem with it too is the EM drive, as they talk about it, isn't scalable. So you can show in a limited system this sort of what looks like thrust as we talked about, but the propulsion of that thrust isn't any different than what we get from like a photonic thruster, shooting photons out the back, which is very, very, very slow. So the idea of even creating some form of fast propulsion off of this system, if it works exactly how they say it does, is still not a thing. So it breaks down in many points, right?
Okay, so let's talk a little bit about what a photonic thruster and then an EM drive is, right? Mm-hmm. So the way that I understand it is you're basically shooting photons out the back of your ship, and then basically the difference in you're shooting a thing out that way, equal and opposite force that's therefore pushing you the opposite way. And over time, you can, the idea would be that you can build this almost like the way that a laser beam gets built up on itself over and over again to generate a lot of thrust from a huge amount of tiny little thrusts.
Exactly. It's a good idea if time is not a consideration, but us humans have limited lifespans and they're pretty small in comparison to astronomical things, right?
Well, so what do you mean by that? Like, what's the difference? What is the difference? Say, are we saying like it'll take 1,000 years for your ship to start?
Well, I mean, not start, but maybe to get up to a speed that you're going to get anywhere fast.
Okay. All right. Got it. Okay.
I mean,
that's what I meant, right? Like it's, you turn the key as a young man,
right?
And then you come back and aged, an old decrepit man. And you're like, oh, we're going 20.
Exactly. And the part about that that's funny too is everybody forgets that that's just speeding up. And I'm assuming you don't want to plow into whatever you're going to at the speed of light or near, right? So you have to turn around and then you have to slow down at that same rate. So, it has problems.
Right. It's, you're driving a truck, right? You start going and then you immediately start braking because you got another light up ahead.
I mean, I have seen people plow their trucks into vehicles and walls and stuff, but that's not the preferred method of traveling someplace.
No. So what would you say, I guess, is our current best bet for, for getting, say, to Mars right now.
I mean, right? I cannot push enough the idea of nuclear energy.
Sure.
There are issues that we need to work with, but people don't seem to understand. Part of it's politicians' fault, part of it's media's fault. But like we always talk about Chernobyl, we don't build those types of reactors anymore because Chernobyl, right? We use different methodologies when we're doing stuff, and even if we're just allowed to move forward with the research on these things, I think that we would find that I don't see, outside of coming up with a way to make like warp fields and that stuff, which we can also talk about because it relates to this too, the idea of negative energy in these systems. But unless you find a way to do that, the only source of propulsion that's really going to work for us, at least on a solar system level, is nuclear.
Got it. Okay. Interesting. It's funny. We did the episode way early on radioactive monsters, which is almost too early in the podcast lifespan for me to even be proud to say people go listen to it. It's right. You get to 100 episodes and you're like, I don't want people listening to anything past 75.
Right.
You're like, anything before episode 75 you can just ignore. Mm-hmm. We'll put that in the vault, so to speak.
Have you come across any of the like the Alcubierre warp field stuff in the zero point energy stuff?
What happens with this for me, at least, and I'm sure it's even worse for you in some cases because you actually have a background in this. Although I don't think you go, trolling the alien Twitters as hard as I do.
No,
necessarily
I avoid
to try to get myself angry on the weekends, right? But what happens for me is someone will see kind of or hear the podcast or hear me on another show or whatever. They'll say, hey, what do you think about this paper? And then they'll send me something that was like written on MS Word that has a bunch of,
paper in quotes,
gobbledygook, just, emojis and ridiculous equations that, if you go line by line, it's like, well, here you said that C was 1 and then here you're saying C is 3. So that doesn't work, and you're like, I don't get it. Like, I just don't understand. So I either get that'll happen, or I will get someone will reach out to me who is way more studied in this than I am. And they'll say, hey, have you checked this out or this or whatever? And then I'm like, I'll add it to the pile of stuff I have to read. But that pile grows every day.
Off the cuff, I am not prepared to talk about this.
No, so right. And then, and then you forget, and then it's like a year later and someone's like, hey, did you ever get a chance to read that? And I'm like, oh no,
yep.
no, not at all. We're doing a series on this new thing now.
Right. Yeah, I get that too. And unfortunately, especially when you start interacting with a lot of conspiracy theorists or quote unquote skeptics, which are different from skeptics, they'll use that as a way of proving to themselves that they were correct, right? Oh, you're just avoiding this. Or I'm like, no, man, you don't understand the amount of stuff that gets put on my pile that I need to go through.
Right. And and the frustrating thing too is with a lot of this, like, we just, we just had a discussion on this stuff, and we at least have heard these terms before.
Right.
Right. And like a quarter of this discussion went completely over my head to the point that I'm going to have to re-listen to this myself. So you have people who, maybe only have a college or high school level understanding of physics. And, it's like, some of those were words, but you're talking about the Casbah effect and,
right.
Calamari's principle, and, it all falls apart. Right. And
right. That's always the problem with any of this quantum woo is it's really easy to pass off stuff as correct because nobody really has the educational background to understand it. There's nothing wrong with that. It's just like anything. You've got to put in your time of learning the background of things to understand it. You can't just jump into it out of nowhere and expect to know everything.
And there really haven't been a lot of recently published really good books on kind of updating the public on where quantum mechanics is.
Right.
Like when I remember I mean, I'm sure you had the same example or the same experience as a kid growing up. Like every other year, there was a new Michio Kaku book,
right,
or a new book by Brian Greene, right? Or there were new books out there that were like, well, this also includes, this one includes string theory. This one includes, all this other stuff. This one includes this. And so there were updates kind of to the realm of where quantum mechanics was, at least for people who were interested enough to buy those books.
Right.
That's kind of fallen off, I think, because, frankly, we're more, I think a lot of the stuff that's being written is more on, kind of nanotech for beginners, right. Or, and of course it's the way, AI or whatever. It's just kind of the way that the public's
public
mindset
interest.
goes.
Yeah, you
exactly.
It's a for-profit industry writing books. Even if you're a scientist, you don't want to write things that nobody's reading, so you write for whatever's big. And you're right, it's AI, it's nano, it's whatever SpaceX, Elon Musk is talking about on Twitter today. You know what I mean? Like,
right. Ridiculous. No, yeah, and it is all this. So I think that there's a bit of a I think there's a bit of a realm there that people could, that would be cool. That would be an interesting thing, I think, to have. And I think podcasts are kind of filling in that void a little bit.
Yeah.
But it's definitely not the same as, science is just having a really hard time. I think we've always had a hard time, but I think it's especially now
right.
talking to the public in a really, but again, there are bigger issues right now than, let's try to get the public to understand like things that are about to kill us, like,
sure.
Anti-vaccine movements right. and climate change. Then we can worry about whether or not they understand the intricacies of quantum mechanics. And so I understand that.
It's interesting because when on the surface, you're absolutely correct. But when it comes down to it, the base issues for all of those things are still the same. And it comes down to a basic, I guess, I don't know how to say it politely, but a misunderstanding of the basis of how science works, how valid arguments are made. There seems to be this idea that we can pick and choose what we want, and that if it agrees with me, then it must be right. And if it doesn't, you know what I mean? There's no analysis of sources. And then the other side of that too is science itself. We have a really big problem with research. The way that our science system is set up in this country is there's not really a lot of money available to do a follow-up study in something, right?
No, there's no money in disproving something.
So you get that initial study that comes out that's really cool, and then it might be 10 years before somebody comes along and tries to repeat that experiment independently.
It's a challenge, and I hope it's one that I think, again, I think that podcasts are filling in a lot of that realm. And the other thing that's cool too is, there are a lot more now channels even that that do stuff that are, it's like science adjacent. It's not, I don't know if you watch on YouTube. I'm a huge fan and proponent of, so two particular channels. One is Primitive Technology, where it's this guy, he builds like, he the other day he finally smelted iron for the first time, and I was like, we in the Iron Age, boys.
It's hilarious that you mentioned that, because I thought you were going to be some like major huge like science thing, and in my mind I'm thinking, I watch Primitive.
No, dude, that's honestly, it is such a good way, because people are like, well, we could never build the pyramids, or like it must have taken us so long, and you're like, no, this guy in, I think, Australia, I've never 100% gotten the answer to that, really.
Yeah,
but I should read his WordPress or something. But it's like, this guy built himself like a hut and sandals and a bedroll, and like he smelted iron. You know what I mean? It's just one guy. And there's other channels too. There's, I watched the other day, some guy in like the Philippines make himself a hot tub.
Right.
Out of mud and bamboo shoots. Like it's,
I heard something, this was a few years ago, and I honestly think it was a stand-up comedian who said it, but it just resonated with me. And he said, we all take things for granted, but think about it. How many people could you pick up and drop in the middle of the woods with nothing and make a cell phone, right? Do all the stuff necessary, all of the knowledge needed to build all the things to come out with a cell phone. And that's obviously a little bit of an exaggeration, but I mean, the premise is true. If anybody listening, think about it. If you were dropped in the middle of a forest right now today, no contact with anybody, what could you do? What could you make? Do you know enough to survive simply? Do you know enough to survive in comfort? And so I kind of took that as a personal challenge. And so, I'm building my own foundry, build my own forge, do all this stuff, learn how to do this, learn how to do that, for no other reason than just, not that I ever think I'm going to be dropped in the middle of the woods, but I'd feel better knowing that I could survive if I was.
It's hilarious. I used to argue that we should give that as a final exam in unit operations, which is the chemical engineering kind of fundamental lab course, right? I always thought that what we should do is we should bring the students out for like a picnic and be like, okay, build me an engine.
Right.
And if you can build me an engine, all it has to do is lift this cup of rocks, right? 5 feet. If you can build me something that can do that, you get an A in this class.
That would be amazing.
It is.
I'd support that.
It's all fundamental kind of thinking, right?
Yeah. And I think that solves one of the problems too that we have with the general public in academia today is there's this mentality of book smarts versus practicality, the engineer versus technician, or the scientist versus the engineer, or whatever, right? And to some point, they're not wrong. There is a lot of book learning that happens. There's people with PhDs who have never set their hands on anything, right?
Sure.
So I think that there is some validity to that question, and I think your proposed solution would fix that.
Oh yeah, there's something to it. I also like the idea of just torturing undergraduate students in the woods by being like, build me an oven. I just think that'd be kind of fun too.
Right.
No, but the other part of this that I think is, so the other channel that I really like is the hydraulic press channel.
Mm-hmm.
I don't know if you've ever seen that one.
Is that the one where they just crush things?
It's so much more than crushing things. He just made a thing. He calls it the Wormmaker 3000, I think is what he calls it. And it's just literally like it's like a cylinder that goes into a piston, or a piston that goes into a cylinder, but it has holes drilled out of it on the top. And so when he crushes stuff, it just makes really long worms. But like his channel too, he's like, well, what happens if I try to, what happens if I try to crush a bunch of stacks of paper, right? And it makes an explosion. Or he's like, well, what happens with this? And, it's just, again, kind of a cool way, I think, of kids and people at least getting a little bit of science in their daily lives.
Yeah.
Doesn't have to be a lot, it's just a little bit.
And doing it in a way that's fun to watch too. I had an idea for a while that I still might do, and I'm going to say it here, and if somebody steals it from me, that's great, because I'd rather watch it than do it. But so I run the rocketry club here for the National Association of Rocketry in my area. And one of the things that I have always wanted to do is make a YouTube channel called Will It Launch, and essentially just strap, rockets onto various items to see how they fly, and then, analyze that and see what we have to do to that thing to actually make it fly. I thought that would always be interesting.
Dude, I would watch the hell out of that. Oh my goodness. I'm all about that life.
Right.
Well, it sounds like we got to start doing some YouTube stuff then, man. I don't know. We've always talked about here starting to do experiments, right? Like that was one of the first things I actually did, back when I was just doing research for Astonishing Legends, was I was like, oh, I can do this experiment to show why what they're saying works, right? And so it was for the Mary Celeste, which is this ship that, they don't know how it sank or whatever, or what happened to the crew. And, it looked like it was just alcohol leaking out of these wooden crates that they had, or caskets that were made out of the wrong kind of oak. The alcohol evaporated, created an explosive atmosphere. And then the people on the ship got freaked out and abandoned ship, and then got overtaken by a wave. That's the, TLDR kind of spoiler, I guess, thing. But the experiment I did was just literally like, the question was, well, why didn't the ship itself burn down then? Or why didn't the caskets burn down? And so I was like, well, if you had an alcohol filled container and then you lit it on fire, the explosion of the alcohol happened so quickly that it won't burn the paper at all. And so I just made like a little paper ship inside a thing of vodka, and then, shook it up and then lit it on fire, and, it didn't burn, and it popped, and It was a lot of fun. But anyways, since that time, I've been like, I would love to do a YouTube channel on just like experiments for these kind of weird things.
Yep.
And I've never done it just because, I mean, first off, who has the time?
It's a lot of time. Yes.
Right.
Yeah. I've had that same mentality, right?
Like iMovie is not easy to use.
No, it is not.
It sucks.
But yeah, I mean, you have like simple things like, I don't know. I just got, I don't know, tired of hearing these arguments about like gas stations, like, oh, they add water to their gas here. I'm like, no, that is not a thing that happens. Let me show you, right? Let me show you what happens when you add water to gas. You shake it up and it's all mixed together for like 3 seconds and then all the water's on the bottom.
Right. And then that's it. And then it won't, it's just, oh God, what a ridiculous thing.
Right. It's just very simple things like that. I'm kind of with you. But again, it comes back to, man, who has time?
It has the time, yeah. Anyway, so quickly before I guess before we wrap it up, I had so many other things I wanted to talk about, and then we hit the hour mark, and I'm like, oh my goodness, we got to have you on again. I love talking to you, man. It's been a lot of fun. But quickly, what kind of stuff have you done on the show that you think someone who's getting into this, some of our listeners always say to us, we love the show. We wish there was, we wish there were more shows like this that did science, and frankly, sometimes, we get people that'll say, well, we wish there was more science, or, we wish there was more ghosts or whatever. And so we always try to point them out to other shows like this. And so yours is one that I point people out to say, hey, here's a show with more science. That's really good. But what episodes have you done recently that you think would be good for people to kind of jump on to listen to?
I've, when I started the show, I did a lot of interviews with academics and scientists and people in industry, and people liked that. But I've started kind of branching out from there into other types of things. And one of the types of shows that we do that seems to have a lot of, I guess, feedback is almost science history. So we did a 3-part bio on Nikola Tesla, and we teamed up with Amber and Andrew from Into the Portal and did kind of the more wooey side of Nikola Tesla too. And then we did one that was another 3-parter on Isaac Newton. And both of those seem to be received really well because people in history and science, especially people of that caliber who are just, way above and ahead of their time, aren't always the most normal of people, to put it nicely. But
no.
So those ones have been pretty good. And then also we did a couple of episodes for NASA's Day of Remembrance for, the Apollo Challenger in Columbia. And people really enjoyed those ones. So I would say if you're looking for science that's not hard science and just maybe even a little bit of history in there, those are some really good episodes that we've had some good feedback for. So
cool. Great. And so where can people find you?
Sure. We're at a-science.com. And then I also do, let's say I'm on Twitter at Physicist Chris, and I do occasional Twitch live streams. I'm starting to do that more. I've kind of created this forum idea where I'll take a couple of people who aren't necessarily heavy in science, and we'll just talk about a subject so we can get kind of an idea of where the general consensus is on something, and then we can expand from there. So those are going to be more live streams on Twitch. So that's twitch.com/physicistchris. And then facebook.com/dash-of-science is our group. You can check us out there, find all the updates. So I hope you guys tune in and listen and enjoy it.
Nice. Yeah, definitely do that. And thanks so much for coming on, and we'll talk again soon.
Yeah, thanks for having me.
Cool. All right. As always, this has been the Mad Scientist Podcast. Thanks so much for listening. We'll be back again soon. I'm not sure when this one is going to drop necessarily, but it's likely going to drop somewhere in the middle of our Unabomber series. So this is just kind of a nice scientific interlude before we get into his mathematics and kind of the science of what he was doing. But thanks again so much for listening. This has always been a Damn It Chippy Productions episode, and copyright the Mad Scientist Podcast. Thank you. Thank you again, dear listeners, for listening to the Mad Scientist Podcast. I have been your host, Chris Cogswell, joined by my co-host,
Marie Mayhew.
If you'd like to contact the show, please send us an email at themadscientistpodcast@gmail.com. That's all one word. You can also follow us on Twitter at Mad Scientist Pod or at Team Giant Squid for Marie. And of course, you can see us on Facebook, on Instagram, and all over the internet as the Mad Scientist Podcast. And again, our logo is the one with the pumpkin head, so it's easy to see.
Mm-hmm.
If you've enjoyed the show tonight, please consider supporting us on Patreon.
where the money that you give to us will help us to promote this show further, to make it better, and just to spend more time making it.
Yes, we love doing that.
We do love doing that. Our logo was designed by Carrie Shaheen. Our web design is done by Desdemona Howard.
Woohoo!
And our sound design is done by Jake Cardinal. Thanks again for listening.
Thank you. This has been a Damn It Chippy production.